Hey everyone, Dr. Mungli here. So this video is all about salvage pathways. So I will be concentrating on purine salvage pathway and pyrimidine salvage pathway. Now first let's understand why do we need to do this salvage pathway, why our cells are involved in salvage pathway. So if you refer my other presentation, which the link for that is there in the description below. So the de novo biosynthesis of purine nucleotides, de novo biosynthesis of pyrimidine nucleotides, these reactions involves lot of reactions, many ATPs are needed. It's a time consuming process, it's an energy consuming process. That is why most of our cells, they also depend on salvage pathways, especially cells like lymphocytes. Lymphocytes are predominantly depend on salvage pathways. Of course, these salvage pathways can go on in other cells like in the liver, it can be neurons, it can be other immunological cells. This can go on there. Now, what is the advantage of salvage pathway? So in the salvage pathway, what these cells will do is they are trying to reutilize the purine bases that are coming from cell turnover process. So whenever the cell turnover occurs, so there will be breakdown of DNA, breakdown of RNA, so the bases are released, nucleosides are released, that is based with the sugar, these molecules are released. So how our cells, they are going to use these molecules if there is a need for new DNA synthesis, new RNA synthesis. If there is no need, these bases are degraded into their metabolic end products like purines are degraded into uric acid, pyrimidines are degraded into carbon dioxide, ammonia, beta-alanine, all these water-soluble products. Now, let's get into purine salvage pathway. What are the enzymes that are needed to salvage these purines? So the purines, the purine bases, which can come from cell turnover or which can, to certain extent, they come from the food that we eat, like the intestinal nucleases, going to break down DNA and RNA coming from the food, and our body will absorb bases or the nucleosides. So what will happen to these bases, nucleosides coming from cell turnover process or coming from the diet? So first let's get to see what happens to adenine. So the adenine is a purine base. So adenine, it is converted into adenosine monophosphate. Adenine is converted into AMP, adenosine monophosphate. So this job, it will be done by an enzyme called APRT. APRT is adenine phosphoribosyl transferase. APRT is one of the purine salvage enzyme, adenine phosphoribosyl transferase enzyme. So what it does, it is going to take PRPP, phosphoribosyl pyrophosphate, gets into this reaction, and inorganic pyrophosphate will go out, and one of the phosphate along with the ribose is attached to adenine, and that becomes nucleotide. Now this is adenosine monophosphate. This adenosine monophosphate can be converted into adenosine diphosphate, it can be converted into adenosine triphosphate. Once you get adenosine diphosphate, ribonucleotide reductase can convert adenosine diphosphate into deoxyadenosine diphosphate, which can eventually be converted into deoxyadenosine triphosphate by specific purine nucleotide kinases. Now, in the same way, so that means we have used phosphoribosyl transferases here, like adenine phosphoribosyl transferase. Now, our another purine base that can we get it from cell turnover or from the food is hypoxanthine. So hypoxanthine, which is another purine base here, it can be converted into inosine monophosphate. Hypoxanthine is converted into inosine monophosphate by an enzyme called HGPRT, hypoxanthine guanine phosphoribosyl transferase. So in this particular reaction, again, PRPP, phosphoribosyl pyrophosphate, gets in, and PPI goes out. Okay, now what will happen to IMP there? So IMP can be converted into AMP there. IMP is converted into AMP, inosine monophosphate converted into adenosine monophosphate. So this job, it will be done by two enzymes actually. IMP will go into adenylosuccinate formation, and adenylosuccinate will be going into adenosine monophosphate formation. So two-step reaction there. So you can see that in my video, purine biosynthesis video. The link is there in the description below. Now another base is a guanine here. So guanine is a purine base which will be converted into guanosine monophosphate. Guanine is converted into guanosine monophosphate done by an enzyme, again HGPRT, hypoxanthine guanine phosphoribosyltransferase transferase, and again sugar phosphate is coming from PRPP, phosphoribosyl pyrophosphate, releasing PPI, inorganic pyrophosphate. Now IMP here, inosine monophosphate, coming from hypoxanthine, can be also converted into GMP by two-step process. IMP is converted into XMP, that is xanthosine monophosphate, by IMP dehydrogenase. XMP is further converted into guanosine monophosphate by transaminidase enzyme or transamidase enzyme. Now that's how you have synthesized nucleotides here. So free bases, adenine, hypoxanthine, guanine, free purine bases are converted into adenosine monophosphate, guanosine monophosphate. These are purine bases, and using two enzymes there, APRT and HGPRT. If there is any defect in these enzymes, purine salvage enzyme here right now, so there can be disorders. Like if there is a defect in HGPRT, it can give rise to a disease called Lesh-Nyhan syndrome, which is one of the commonly asked question in all kinds of exam. And Lesh-Nyhan syndrome is it follows X-linked recessive pattern. There are so many clinical signs and symptoms which will appear in this, and I have a video on Lesh-Nyhan syndrome. Link for that video is there in the description below. You can take a look at that video at the end of this video. Now let's look on to pyrimidine bases. Like pyrimidine bases coming from cell turnover or degradation or from the food. So we have cytosine, and we have uracil, and then we have thymine here. So these are pyrimidine bases. So cytosine and uracil, they'll be converted into their nucleoside form. Cytosine can be converted into cytidine, and uracil can be converted into uridine. And this conversion of cytosine into cytidine, uracil into uridine, it will be done by pyrimidine nucleoside phosphorylase enzyme. And during this process, ribose 1-phosphate gets into the reaction, and inorganic phosphate will go out. The job is done by pyrimidine nucleoside phosphorylase enzyme, specific pyrimidine nucleoside phosphorylase. Generally, these pyrimidine nucleoside phosphorylases, they have a general specificity, not really specific, so they are general enzymes. They take cytosine into cytidine, uracil into uridine, so same process will go on. Ribose 1-phosphate getting into the reaction and inorganic phosphate going out, and nucleoside is synthesized. Base cytosine converted to cytidine, uracil converted into uridine. In the same way, thymine is converted into thymidine, and the job is done by thymine nucleoside phosphorylase enzyme. So during this process, deoxyribose 1-phosphate gets into the reaction, and inorganic phosphate will go out. So this is basically thymine nucleoside phosphorylase enzyme. So like this, pyrimidine nucleosides or pyrimidine bases are also be undergoing salvaging process, and thereby nucleosides are synthesized. Once you make nucleoside, you can make nucleotide by specific pyrimidine nucleotide kinases. Like cytidine can be converted into cytidine monophosphate by specific kinases, cytidine kinase enzyme. Uridine is converted into uridine monophosphate by uridine kinase enzyme, and thymidine is converted into thymidine monophosphate, that is done by thymidine kinase enzyme. Now, going with these enzymes, so majority of time when these kinases, so the uridine kinase is the most specific enzyme, and this is the one the enzyme which is highly active, Because once you make uridine monophosphate, still you can make uridine cytidine triphosphate and thymidine triphosphate. You can take a look at my video on pyrimidine biosynthesis. The link is there in the description below. So it's about uridine monophosphate, which is the common molecule, because uridine monophosphate, which is further converted into uridine diphosphate and into uridine triphosphate. Once you make uridine triphosphate can be converted into cytidine triphosphate, and uridine diphosphate here, it can be converted to deoxyuridine diphosphate, which is further converted into deoxyuridine monophosphate, and deoxyuridine monophosphate can be converted into thymidine monophosphate, deoxythymidine monophosphate. All that I have explained in the pyrimidine biosynthesis video. That means this uridine monophosphate formation is that's the most important one, because uridine monophosphate can give rise to other pyrimidine molecule nucleotides. Anyway, now the thymidine is converted to thymidine monophosphate. This job is done by thymidine kinase enzyme. I'll write it as TK here, thymidine kinase. Now the activity of thymidine kinase, increased activity of thymidine kinase, it is an indicator of high levels of cell proliferation, because this is the one which is going into DNA synthesis. It is going to take thymidine into thymidine monophosphate, which will be converted to thymidine diphosphate and thymidine triphosphate. So high levels of activity of thymidine kinase indicate it's an S phase of the cell cycle or the synthetic phase of cell cycle. And also whenever there is high levels of DTTP, that is deoxythymidine triphosphate, so it will have a negative effect on thymidine kinase enzyme. High levels of deoxythymidine triphosphate is going to have an inhibitory effect on thymidine kinase enzyme, thereby decrease the activity of enzyme. Now this is all about pyrimidine salvage pathway. This is the entire thing is pyrimidine salvage here. So now let's look into little more details on purine salvages, because I have explained purine salvages, two enzymes here basically. Adenine into adenosine monophosphate APRT, hypoxanthine into IMP by HGPRT, guanine into GMP by HGPRT. Now what will happen to these pyrimidines? Whenever the cell undergoes degradation or cell turnover is going on, so or when adenine is converted adenosine monophosphate, and if the cell doesn't really need this, so when the cell turnover is going on, what will happen to adenosine monophosphate? Now the adenosine monophosphate, it will be converted into adenosine monophosphate converted into adenosine by releasing inorganic phosphate, and the job is done by 5' nucleotidase enzyme. So the 5' nucleotidase enzyme is releasing inorganic phosphate from AMP and convert that into adenosine. Now what will happen to adenosine? Adenosine can be converted into inosine. Adenosine is converted into inosine. So this job is done by adenosine deaminase enzyme. So during this reaction, there will be release of ammonia molecule NH3+. So that's how the adenosine is converted into inosine. Now what will happen to inosine here? Now the inosine is converted into hypoxanthine. So I'm going to use a different color here. So inosine is taken into hypoxanthine formation, and the job is done by purine nucleoside phosphorylase enzyme. So the name of the enzyme here is purine nucleoside, because this is a nucleoside, inosine is a nucleoside, phosphorylase enzyme. Phosphorylasis process is going on here. So that means you are going to add inorganic phosphate into the reaction and release that ribose. That inosine has got a sugar there, so you are releasing sugar by adding phosphate. So you add inorganic phosphate, Pi is added into the reaction, and then it will release ribose 1-phosphate. Ribose 1-phosphate is released, and that's how the sugar is released from the nucleoside. Convert that into a free base. So inorganic phosphate inserted into the reaction and releasing ribose 1-phosphate. So note that inorganic phosphate is not part of the base here. So the nucleoside is converted to base, and ribose 1-phosphate is released there. So ribose 1-phosphate can be converted into ribose 5-phosphate, and that again get into PRPP formation, phosphorybosylpyrophosphate pyrophosphate formation. So in the same way, guanine, which is converted into guanosine monophosphate, and the guanosine monophosphate can be converted into guanosine, and that is done by again 5' nucleotidase enzyme. So that means there will be release of inorganic phosphate in the reaction. Inorganic phosphate is released. Now, what will happen to the guanosine? Guanosine is a nucleoside there. So this guanosine can be converted into guanine. So it will be taken back into the guanine formation. If the cell wants to make a new DNA and RNA synthesis, guanosine is converted back into guanine, that is a free base. So done by purine nucleoside phosphorylase enzyme, because you need to release sugar from the guanosine, which is a nucleoside, and to make a free base. So how to release that sugar? So you add inorganic phosphate into the reaction and release ribose 1-phosphate. So the ribose 1-phosphate is released there, and you got a free base. And this free base, it can go into new guanosine monophosphate formation, or if the cell doesn't want it, the guanine can go into degradation process to make uric acid. Hypoxanthine can go into degradation process to make uric acid. Adenine can go into degradation process to make uric acid. So the degradation product of purine is uric acid. Anyway, so this is how the nucleosides are converted back into free bases. Now let's get into one of the important thing here, that is adenosine. So adenosine, there is another fate of adenosine. Only nucleoside, only purine nucleoside that can be directly phosphorylated is adenosine. Remember, adenosine is also, it is a neurotransmitter. It's one of the inhibitory neurotransmitter in the central nervous system. Anyway, that's a different point there. Now, what will happen to adenosine? Adenosine is taken back into adenosine monophosphate. Adenosine can go back into adenosine monophosphate if the cell wants to make adenosine monophosphate. This job is done by enzyme adenosine kinase enzyme. So this is the only reaction. Adenosine converted adenosine monophosphate, where phosphate is incorporated into this nucleoside to make nucleotide. This is the only nucleoside that we have that can be directly phosphorylated. We cannot phosphorylate directly inosine back into inosine monophosphate, guanosine back into guanosine monophosphate. That process cannot go on because simply we don't have inosine kinases, guanosine kinases, but we have adenosine kinase enzyme. That is the specialty about it. So, and also one thing that I forgot here, so IMP can be converted to inosine there by same 5' nucleotidase enzyme, and inorganic phosphate is released. Anyway, now adenosine kinase, once it is converting adenosine into AMP, so AMP can go into ADP and ATP formation. Now the AMP can also be converted back into inosine monophosphate by AMP deaminase. If you are degrading this, so AMP into inosine monophosphate by AMP deaminase. Basically there will be release of NH3 there. Okay, so this is how the interconversion of all these molecules will go on depending on the cellular needs. One of the applied aspect, one of the clinical aspect here is, what if there is a deficiency of adenosine deaminase enzyme, which is converting adenosine into inosine? What happens? What if there is a deficiency of adenosine deaminase enzyme? So that will give rise to a disease called a severe combined immunodeficiency disorder, that is SCID, SCID, severe combined immunodeficiency disease. And around 50% of the cases of severe combined immunodeficiency disease is because of autosomal recessive deficiency of adenosine deaminase enzyme, which will give rise to both the B cell and T cells are defective. I have a video on severe combined immunodeficiency disorder. Link for that video is there in the description below. So this is all about purine salvage pathway and the pyrimidine salvage. I hope this video has helped you in understanding how the purines and pyrimidines are undergoing salvage process, thereby time and energy is saved for the cell. So this is basically interconversion of free bases, nucleotides, nucleosides, depending on the cellular needs and using specific enzymes. Some of the enzymes are like phosphoradesyl transferase, and then we have purine nucleoside phosphorylase enzyme, 5' nucleotidase is there, adenosine deaminase is there, and adenosine kinase. This is for purine bases. For the pyrimidine bases, we have pyrimidine nucleoside phosphorylase enzymes, and specific kinases are there, and thymidine kinase there. So that's all about it. So thanks for watching, and if you like this video, give thumbs up, and also for regular updates and also for this kind of videos, so you can consider subscribing to this channel. Thanks again, and see you in my next video.